What we're going to talk about today initially is your next programming assignment, which is implementing a fair semaphore via the specific notification pattern. And so we're going to talk about that. And whoops, for some reason that doesn't show up well, but if you take a look at the actual PDF version of this that I'll put up on the website, it'll give you the link where to download this paper. And this paper describes the pattern and has some examples, especially listing 3 that are useful as a way to figure out how to do the assignment. I'm, of course, going to walk through everything and give you a sort of a high-level pseudocode-like view of what's going on as well. So let's start off with a quick recap of what fair semaphores mean. So if you have a fair semaphore, it means that when threads, a group of threads, call acquire on the semaphore, or on a fair semaphore, they obtain the permits in FIFO order. That's what the meaning is. Now, FIFO order is something that has a very specific meaning in this context. In particular, it applies to internal points of execution within the implementation of the semaphore methods. So in particular, you could have a situation where one thread actually calls the invoke method before another thread, but the other thread would actually reach the ordering point before the first thread. And that just has to do with the non-determinism of concurrency. So concurrency is often non-deterministic, and things don't always occur in exactly the right order. So in this case, FIFO ordering has to do with a so-called ordering point. What's an ordering point? An ordering point is something like waiting on a lock, right? So when you get to that point, that's when this starts to matter. And we'll talk about that. It's a very subtle point, but it's an important distinction to make. So let's talk about the specific notification pattern. So the context for this pattern is you have a group of threads in Java. This is a Java-centric thing here, although you'll see that other languages would have a similar issue if they were implemented in the same way. And you want these threads to be able to cooperate to synchronize their use of some shared resource or resources in a shared way. So going to our Palantir example, we've got a bunch of threads, and we want them to be able to access some number of resources, where the resources are the Palantir. The problem is that Java's built-in monitor objects, which we've talked about a couple of times, you've got some experience using that in one of the programs. We'll talk more about it shortly. They don't give you, the app, any control over the order in which the threads acquire a resource. It's what's called, in the pattern description, haphazard notification. So the order in which threads are awakened to access the resources is up to the implementation of the virtual machine and the hardware, not up to your application's control. Now, sometimes you don't care, but other times you do care. And so if you care, then the built-in monitor object semantics are not sufficiently precise in order to give you control over those kinds of things. In particular, selecting a thread to run after notify or notify all is called is not defined by the spec. In other words, the operating system, the implementation, the virtual machine, the hardware, they're free to do it any old way they want. So selection is not mandated. Neither is scheduling. So once a thread has been selected, then the order in which things actually run, especially on a multi-core system, is totally an implementation detail. So that's sort of the problem that we're starting with. And as I mentioned, there's some situations where that's not sufficient. You really want to have great control over this. So if you need control, if you need that fine level of control, then one way to do it is to apply the specific notification pattern. And for some reason, this link shows up better, so take a look at that. And let's talk about what the pattern does. What the pattern does is it provides a non-haphazard mechanism, in other words, a specific notification, not a haphazard notification mechanism, for selecting and scheduling threads. That's one thing it does. And it does this by designating precisely or exactly which thread in a group of waiting threads should be the next to proceed after notify or notify all is called. So it's about selecting the thing to go and then making sure that that's the one that gets to run next. So first I'll give you a sort of a high-level outline of how this works, and then we'll walk through it in a more detailed view. So what it's going to do is when a thread wants to acquire a semaphore, rather than doing it in a haphazard way, it will actually have the thread go to sleep on a wait. It'll go to sleep by calling wait on a monitor object. So we'll talk a bit more detail about this. Now, for assignment 2B, the undergrads use monitor objects. The grad students will use these, they're called waiters or wait nodes or whatever, and they effectively are monitor objects by the way that they have a reentrant lock and a condition object in them. So what we'll end up with here, as this happens, is we'll end up with a FIFO queue of these wait locks, and that's what's going to be used to keep track of the order in which things are going to run. So one monitor object will be used for each thread that must be individually notified. So each thread that's going to be waiting is going to use the monitor object in its particular wait lock. So we're going to have a queue, an ordered queue of these wait locks. And then the threads that wait on their monitor objects are notified in, first out order. So that's how we're going to ensure that things are going to wake up at the right time, because the thread that's at the front is the one that's going to be notified first, and the thread that's next is the one that's going to be notified next. So we no longer have the problem of haphazard notification. And I was trying to think of like how we could actually act this out if we were, if this is like an acting class, we'd get people to line up and we would, take turns notifying each other, and you could see how it worked. I felt that was a little bit too contrived, but you get the idea. You have a queue of things, and you wake them up in the order in which they're waiting. All right, so that's the big picture view. Any questions about that? We're trying to ensure that things happen in the right order. Now, at face value, that seems pretty simple, right? It's like, oh, that doesn't seem that hard. So now I'm going to talk through the implementation details, and it's actually very subtle and very tricky to get this right, and that's why I want to spend a little bit of time on this, so that you'll be able to do it in your solution. And we're going to do this with a visual analysis of the fair semaphore. And we're going to start by talking about the acquire operation, and we'll focus on thread T1 and thread T2. We'll then talk about another acquire with thread T3, and then we'll talk about releasing with thread T4. And you'll see why I broke it down in that way, because it helps you work through each of the steps. Now, this is going to be a visual analysis, because if I gave you the source code, you wouldn't have anything to do for your assignment. And interestingly enough, if you learn to read these diagrams and follow the pseudocode, it really walks through the implementation, but it's very subtle. And so it's going to take quite a bit of thought to make it work properly. So here is the picture that we're going to use, and you'll see this over and over again on each slide. So this is an icon that represents a monitor object. And here's basically the way it works. You have this little region outside here. This is kind of like the waiting room. And you enter the waiting room, the monitor object. It's kind of like when you call a method that's synchronized. You call the method. So you're kind of in, you've committed yourself to being in this experience at this point. It's like the waiting room. But you're not yet in the critical section. Remember, there's only one thread at a time that can be in the critical section in the monitor object. And then this funky thing over here is kind of the waiting area where you're going to be kind of parked off to the side when you can't make any progress. And we'll talk a bit more about that later, but that's kind of the high-level view. And down here is one of the things that we're going to be protecting with our critical section, which is the count of available permits. All right, and you'll see how this unfolds as we walk through this. So we're going to start out our little example by creating a fair semaphore with a single permit. So you can see it has a count of 1. We make this. Let's assume that that's done somewhere, in the constructor or whatever. And then thread T1 comes along, and it wants to acquire this semaphore. Well, at this point, the count is 1. So this should work immediately because there's no waiters, and there's a count of 1, right? So we can go in there and grab the semaphore. All right, so what's going to happen here is when acquire gets called, then now I'm kind of stepping into pseudocode of the implementation. We're going to acquire the monitor lock. So if this is done with built-in monitor objects, how are we going to acquire the monitor lock? What's the syntax that it's going to look like? Synchronize, and what are we going to synchronize on? This. Synchronize this. So that's what we're doing here, right? And whenever you see this picture like this is this, right? This is the monitor, this is the fair semaphore. And it gets a little confusing because we're going to have a linked list of monitor objects, which I call wait locks. But that's not, that's a different thing. This is the fair semaphore. So when we talk about synchronize this, it's going to be the fair semaphore object, which is being synchronized. OK. So the first thing we're going to do is we're going to synchronize access to MonitorLock. Now, why do we need to do that? We need to synchronize access because we're going to access shared state, like the permit count and the queue. OK? So we have to make sure that those things are protected, because otherwise we'll have race conditions and bad things will happen. Yes?
Where's the waiting curve?
Where's the what?
Waiting curve. Waiting queue.
Oh, we'll see where the wait queue is. The question is, where's the wait queue? We'll see. That's also accessible from within here. OK, so if the queue is empty, all right, remember the lock is held, we've synchronized this. If the queue is empty and the permit count is greater than 0, if those conditions are true with the lock held, then this is the fast path, right? Nobody else is there. We got there first. We simply decrement the count and we return. So we're done. That's the easy case. But notice, as a consequence of this, the permit count is now 0. OK, at this point, we are going to step out and exit the monitor's critical section. And so we're done. Thread T1 got its resource. It's got its semaphore. It's off doing its thing. It's gazing at Palantir, or a Palantir, or whatever it's doing it. It's finished. So life is good for it. All right, so now, same condition. We have a semaphore with a count of 1. This is not repeated. This is just showing you the context. We had a semaphore, a fair semaphore with a count of 1. Now thread T2 comes along, right? T1 is off doing its thing, has not released anything yet. And now thread T2 is going to try to get a permit. Except in this case, the count's 0. So now we can't do the fast path anymore. So this is where it gets a lot more tricky. And this is really subtle. And I'll see if I can break it down for you. What's going to happen is this thread. Notice, by the way, T2 has not entered the critical section yet. It's still outside of the critical section. So the critical section is the lock. This lock has not been acquired. We're going to go ahead and create a new wait object. We're inside the monitor object, but we're not inside the monitor object's critical section. That's the key crucial thing to remember. So we go ahead and create a wait object. For the undergrads, that's just a Java object. It needs to be nothing more complicated than good old object. You probably often wonder, what the heck do you do with an object? Well, here's a place where you can actually use an object. The grad students, it'll be a waiter. So you'll have to have a linked list of either objects or waiters, depending on whether you're doing the undergrad or grad version. And you'll make a new one of these things, which we're going to call a wait object. And this can then be synchronized upon and queued in a wait queue, which will be, of course, in here somewhere. All right, but keep in mind, this happens outside of the critical section. Now what we're going to do, and this is kind of funky, we have created ourselves a new wait object. And now we're going to go ahead and synchronize on it. And the reason we're going to do that is because we do not want this object to be deleted by someone coming along and releasing things. So we've got to make sure we lock it so that nobody else can get in it and do anything to it. So the lock is acquired, the wait object is acquired. And now, with the wait object lock acquired, synchronized on, now we have to synchronize on the monitor lock of the fair semaphore. And the reason we have to do that is because we're about to access the shared state, the wait queue and the permit count. And those things have to be accessed with the lock held. If the lock is not held, you'll get race conditions. All hell's going to break loose. Not a good thing. All right, so keep in mind, this guy has been synchronized, and now this guy has been synchronized on. And what we're going to do is then we're going to go ahead and add the wait queue. Sorry, we're going to add the wait object that we just created, the one that was available here. We're now going to go ahead and stick it into the wait queue. So Yifan had asked, where's the wait queue? Well, here's the wait queue. We finally got a wait queue in there. So now there's the wait queue. And we stick this wait object at the end of the wait queue. In this case, there's no other nodes, so we put it at the beginning, but it's at the end, at the beginning and the end. And then we go ahead and we release the fair semaphore's monitor lock and leave the critical section. So we're not leaving this thing, we're leaving that thing. So we've now released the monitor object's critical section for the fair semaphore. And this is really important. If you do not do this, if you do not leave the fair semaphore's monitor lock, if you don't step out of its critical section, you're going to end up with deadlock on yourself. And I suspect a number of you will not do that when you do your first implementation, and when you run the fair semaphore unit test, it will just hang. You'll be like, what the heck's going on? What you've done is you've forgotten to release that lock. OK, so at this point, the critical section for the fair semaphore is still open, which is fine. And however, the wait object is still synchronized. And then what you're going to do is you're going to go and call wait on the wait object. And remember, whenever you call wait on an object that's a monitor object, which is what this thing is, it's a monitor object. It's just an object, but it's a monitor object. That will do two things. What are the two things? When you call wait on a monitor object, what are the two things that happen atomically?
Releases the lock and goes to sleep.
Bingo, exactly. It releases the lock and goes to sleep. So at that point now that monitor object, the wait object's monitor lock, has been released. It's safely in the queue, which has been protected because we had earlier allocated, or we had earlier synchronized on the fair semaphore's critical section. It's safely in the queue, and the thread that just inserted it is now waiting on this wait object. Now, how do you think it's going to be not waiting on that object? What's the situation under what's going to happen to get it to be not waiting? Right, but something else has to happen for it to stop waiting. Something will notify it. Another thread will come along and notify it. OK. All right. So, OK. So that's the case. At this point, we've got one item in our queue. We're blocked. Thread T2, as you can see here. Oh, and by the way, if you notice if you're watching carefully at these diagrams, notice that when we call wait, we move from running in the critical section to releasing the lock and blocking on the monitor condition for this particular monitor object. So that's what we're doing there. OK. So that's the basic idea. Very subtle. Not a lot of lines of code, but man, you got to figure out where those lines of code go. Now here's something even more subtle. Anybody here ever watched the TV show Kungfu? It's probably the wrong generation. Anyway, it's a great TV show. And if you want to amuse yourself, go Google on YouTube, "Snatch the Pebble from My Hand." Right? So the thing was, when you could, it was a young monk who was training at the Shaolin temple, and he had like a master, and the master would say, since he was a little boy, he'd say, "When you can snatch the pebble from my hand, grasshopper, it will be time for you to go," right? Because you've achieved greatness. So when you can figure out what I'm about to talk about and feel you totally understand it, you've gotten sort of to the next level of like enlightenment in Java Kung Fu or Java concurrency Kung Fu. All right. So here's the interesting question. A thread is blocked waiting to acquire a permit, and that thread gets interrupted. What the heck should happen, right? So that's the thing we're about to talk to. This in my mind is the most complicated part of the whole thing. Again, it's a handful of lines of code, but thinking through what those lines should be is tricky. So let's think about that. What should happen, right? We've got somebody on a queue. He's waiting, or he or she, whatever gender you want the thread to be. The thread is waiting, and somebody interrupts that thread. What should happen at that point? Right. So it's going to be removed from the queue. We want this. Let's assume, for sake of argument, there's one item. We want this item to be removed from the queue, and we want the interrupted thread to know it was interrupted, right? So it's got to receive an interrupted exception, and we don't want it to actually get a permit, right? So we want the permit to be left, right? We don't want that particular thread to be to get a permit because it was interrupted, right? It never really got a permit. All right, so that's what we want to have happen. So if you think about how this is going to work, we're on this queue, we get an interrupt, the interrupt is going to show up. How's the interrupt going to show? How are we going to know we were interrupted, first of all? Remember, we were blocked in a call to wait. We're going to get the interrupted exception, right? So the interrupted exception occurs, and that will be caught, right? You're blocked in wait, an interrupted exception occurs, you catch the interrupted exception. Now you've got to do some cleanup. Remember when we talked about how we handle Java exceptions? Earlier we talked about Java exception handling, and we said there was different ways of handling exceptions, and one was to ignore exceptions, which we don't want to do here. The other was to do some cleanup stuff and then bail out, right? Or rethrow the exception. So that's what we're going to do here. We're going to clean up. So what do we have to do? How are we going to clean ourselves up? So we put something in a queue, we got interrupted, we want to, sort of leave no trace. We have to remove the wait object from the queue. All right, well that's interesting, but where is that wait object? Well, in this case it would be at the head of the queue because there's only one item, but in general it could be anywhere in the queue. So we're going to have to call a method that removes something from a linked list. And I'll give you a hint. It's called remove. So you call remove, you give it the object you want to remove. So that makes some sense, but it gets even more tricky. Because what happens if we go to remove ourselves, our wait object, from the queue, and it's not there? What does that mean? Right? We put it there, we got interrupted, we try to remove ourselves. If we remove ourselves, we're fine, we just rethrow the exception. But if we don't find ourselves in the queue, what does that mean? Yes, we got a permit, right? But it's even worse than that, right? Because what has happened here is that somebody else has come along and done a release, and that's caused us to get taken out of the queue. But then because of the non-determinism of concurrency, between the point where we were taken out of the queue and when we got interrupted, there was a space of time, and the lock wasn't protecting that. That could certainly happen. So at this point, we've been given a permit, but we're actually not really we don't really have a permit. We've been interrupted, right? So interrupts take precedence. So what we have to do in that case is, because we're not going to actually have a permit, we're going to have to call release before we rethrow the exception. And that way, that will give the permit back and permit somebody else to go ahead if they're waiting. So this is really subtle. Again, it's only a handful of lines of code, but reasoning about what happens when an interrupt occurs is very subtle. And you have to make sure all this stuff works properly in the context of concurrent access. So that's the tricky part. So here's kind of the way this is going to look. When you're interrupted, you have to reacquire the fair semaphore's monitor lock, and you need to do this in the exception catch clause, right, the thing that caught the interrupted exception. And the reason you need to redo this is because you've got to access the queue, and the queue has to be locked. Anytime you access the permit count, anytime you access the queue, the monitor lock for the fair semaphore has to be locked for this. You'll then attempt to remove the wait object from the wait queue. If you succeed, then proceed to the next step. If you don't succeed, then it means that another thread must have released it. So you need to go ahead and call release to unblock another thread or give back the permit. That's what Duncan was just saying. In any event, after an interrupt has been raised, you caught it, you clean up, you then need to rethrow that interrupt exception so it gets propagated back to the caller so that they know that an interrupt occurred and they don't have the permit. Okay. Really, really, really subtle. The hardest part there is just figuring out what should happen under those circumstances. The actual code isn't too hard, but it's figuring out where to call it and how to lock it that gets tricky. All right, so let's assume that the interrupt didn't occur, so we're still in a situation where we've got one item on the queue. And now thread T3 comes along. And we want to have this thread also block because there's something in the queue already, right? There's no point in going any further. There's no point in doing anything else if there's already something in the wait queue, because that means somebody else is waiting. So there sure as heck's not going to be a permit to acquire. This particular implementation, by the way, notice how permits never becomes negative. Instead, the number of items in the wait queue is sort of a surrogate for a negative count. So the count is always 0 or higher, and then we have a linked list of waiters, which is kind of the moral equivalent of being negative numbers for this count. All right, so what happens here, this is actually very much like we just saw before. We create yet another wait object that can be synchronized upon and queued. We go ahead and synchronize on the wait object so it's not prematurely released. We then go ahead and synchronize on this in the fair semaphore so we can update the wait queue safely. We don't care about the permits now, we care about the wait queue. We then go ahead and add the wait queue, add the wait object to the end of the wait queue. So now we have wait object A, which used to be just this one. And now we have wait object B behind it. We got to put it in FIFO order, so that's why we use a linked list. We're going to go ahead and put it at the end. Then we release the monitor object and leave the critical section. So at this point, permit count is 0. We have 2 items waiting in our wait queue. The lock has been released. Something else will happen. Once again, make sure that you do this by having the wait call made on a synchronized wait object, but you can't hold the monitor lock. Otherwise, you'll get self-deadlock. That's the monitor lock of the fair semaphore. That's the subtle part. Same thing as before. I'm just reiterating it. Yes, Anne?
When you call wait, it won't automatically release the monitor lock?
Great question. That is indeed the big question. So remember the following. We'll talk more about this in detail later, but the thing to remember is that with Java objects, which we're using here as monitor objects, a Java object only has one wait lock and one wait condition. And so anything that you synchronize will only affect that particular one. And so the tricky part here is if you were to hold the fair semaphore's monitor object, if you had that held, and then you were to go ahead and call wait on the wait object, that would release the lock on the wait object, but not on the fair semaphore. So that would still be locked. And that's the problem you're running up against. That's why you can never hold the fair semaphore's monitor lock across calls to a wait object's monitor lock, to wait on that, because it'll only release one object. That's one of the reasons why there's other things in Java like condition objects and so on. We'll talk more about that when we get to concept of multiple wait sets when we talk about condition objects. So yeah, that's the subtle part in this whole thing. If you take a look at the code in the specific notification pattern, he shows how to do it, but he doesn't go into the details of why you need to do it. Some of the other links I'll show you will go into more detail about that. All right, but that's a really good question. Very important thing to understand. The last piece of the puzzle here is thread T4 comes along. This could be T1, by the way, but it's some other thread that's not thread T2 or T3, which are waiting, blocked. And thread T4 will release the semaphore, and what it'll do is because it's the specific notification pattern and not haphazard notification, it will release the object / thread that's been waiting the longest, which is the one that's in the front of the queue, right? So in this case, that's thread T2 that's waiting on wait object A. So it's going to release, that's what we want to do, is get that guy released. Now, mercifully, unlike acquire, which is really subtle in all these crazy nestings of synchronize this and synchronize that and dealing with exception handling and so on, mercifully, release is a lot simpler. In fact, if you really do release correctly, it's very straightforward. So what you do here is, first thing you need to do, we're about to check the wait queue. And anytime you check the wait queue, you've got to acquire the fair semaphore's monitor lock, right? So we're going to synchronize on this. That's the first thing we do. That lets us get into the critical section in the first place. And then, this is kind of cool. If the reason why we're using linked list is because of the following thing. There's a method on linked list, and I'll let you guys figure out which one it is, that will check to see whether there's an item in the linked list or not, without blocking. If there is an item, it'll return it to you. If there's not an item, it'll just return null. So we're going to use that method. And so with the lock held, with the fair Semaphore's monitor object lock held, we're going to check to see if there's anything in the queue. Let's assume there is something in the queue, as we have here. So if there's something in the queue, we're going to take it out of the queue. And what we get, of course, is a monitor. We could get a Java object, which we're using as a monitor object. And so in this case, and this is really subtle, but it's very cool, there's something in the queue. We're going to notify it so it can make progress. So there's no point in incrementing or decrementing the permit count because it's a wash, right? We're releasing it, but then we're also immediately turning around and giving it a chance to run. So it's kind of like implicitly incrementing and decrementing in one fell swoop. Well, if you're going to increment by 1 and decrement by 1 atomically, just leave it where it is, right? There's no point in changing the count at all. So the permit count stays exactly the same. We've now got our fingers on this wait object. And then we go ahead and we acquire the monitor lock on the wait object because we're about to notify it. And you have to notify with the lock held. And then we go ahead and we tell the thread that's blocked, remember the one that's waiting, this thread, in this case it's T2, we tell T2, you can proceed. And we do that by notifying it. We say notify this wait object, and that will then start that in motion. And now it's got a permit, so we give it its permit. So the funky thing about this is we're actually using release to wake up the right thread, and we're handling all the mechanisms of permit counts and so on by leaving them the way they were before. We're leaving that as it is, and the thread that's awakened has nothing else to do except start running. So all the work was done behind the scenes by release, which is kind of funky, but it greatly simplifies the synchronization, believe it or not. Yes, Anne?
So when the wait object calls wait, will it be inside of a while loop to check if there's
Good question. So I've been telling you, one of the things you often do, and you sort of tell people a general rule, and then you give them an exception, right? So I told you almost all the time that you wait in a loop whenever you deal with wait, right? You typically wait in a loop because the condition may not actually be satisfied by the time you loop back around again and check. This is an exception to that rule. And the reason for that is each thread has its own wait object. And so the only purpose of that wait object is to wake up that thread when it's been released. So actually in acquire, which I think is where your questions come from, acquire doesn't use a loop. In fact, if it used a loop, all hell would break loose. The only place a loop would be used is in the acquire uninterruptibly method. But that's a different use case. That's just to make sure you don't get interrupted by interrupts. So no, there's no loop there. Once you're either interrupted or you're given the permit and you do your thing. This is like the one exception to that rule. OK, so we wake the other thread up, and then the other thread can go off and do the thread's thing. Now we have to unlock the wait object's monitor lock, so the thread that's waiting can continue, right? We're going to release that. And then the last thing we do is we release the lock in the fair Semaphore's critical section so it can go ahead and let somebody else in. So that's the case where we've actually got something in the wait queue. If there's nothing in the wait queue, then all we do is just increment the permit count by 1 because there was nobody to wake up. But we're going to give back a permit so somebody else can come along later and acquire it. OK, so that is a walkthrough of the logic steps in this assignment. Now,